Welcome to our technical presentation of Lab 2 for ECEN 160. This presentation is brought to you by Coby Carter, Justin Waite, and Bud Wortham.
Hello, my name is Coby Carter. I am a computer engineering major. I'm really interested in building and repairing computers since my dad was an IT guy for the majority of my childhood. I served my mission in Tijuana and I got back last June.
My name is Justin Waite, and I am a computer science major. I love web application development, and I specialize in back-end design and development. I married my best friend McKenna just 6 months ago.
Hi everyone, my name is Bud Wortham. I am working on a software engineering degree. I'm a big-time gamer and I hope to work on gaming engines when I graduate next year. My wife and I have been married for 2 years and our baby girl is 11 months old now. Our main goal for this slideshow is that we want the class to learn that Conf maps are an efficient tool to reduce Boolean equations in order to minimize cost for a system. Alright, let's go and start with something familiar. Truth tables we've already done a couple times before. We know that one of the things we can learn is the sum of products. And another thing that we can learn is the midterm expression. Now the midterm expression is important because that's where we get the numbers next to the columns from, which we will be using later on for Conf maps. From our last slide, we were able to determine our SOP from the truth table. Now let's go ahead and reduce that. Now with reducing, you have to go step by step in a process. You got to get everything together, simplify it, rework things around, simplify things a little bit more, and you keep going until you finally get to the lowest possible equation. And the main problem with reducing it this way is that it does take time. Now the question is there a way to do the equations quicker? Is there some form of method? The answer is yes, that's for Conf maps. Now a Conf map is a different form of writing a different way of writing a truth table. It is commonly used to simplify identifying adjacent min-terms and max terms. And what we'll do with a Conf map, each spot has a particular min-term or max term. And it's used to map out where we need to put the ones and zeros from the equation. Now that we have where they're supposed to go, we can take our min-terms from earlier and place them in there. Once we place our ones and zeros into the Conf map, how do we reduce the equation? Well, there's a four-step process or a four-step algorithm. The first step, enumerate all prime implications in the K-map, identify which are essential and which are not, add all essential prime implicants to the solution. If there are still uncovered ones in the map, choose a minimum set of non-essential prime implicants to cover the remaining ones. Now the question is, what's an implicant? Well, first off, an implicant is a group of ones in a K-map which are adjacent to one another and can therefore be circled. A prime implicant is the largest implicant which can be created with respect to a given one in the map. An essential prime implicant, a prime implicate which must be used in any minimum solution of the K-map.
There are many advantages to using Carnot maps. There are often fewer steps involved. It is easy to simplify large truth tables. And because K-maps follow an algorithm, it is possible to develop applications or tools for making K-maps and deriving equations from them. Of course, it is important for us to know how to make Carnot maps by hand before we start using tools to do our work for us, but this helps highlight their potential nonetheless. This is an example of such a tool. The first thing you do is complete the truth table by matching the results with the ones given us in the lab. Once the table is filled out, the midterm expressions are highlighted in the Carnot map, and the simplified equation is displayed on the screen.
The circuit created using the gigantic sum of products solution that we found earlier can be created in Logisim. At the right, we have the circuit that has been created using that sum of products equation. As we can see, it's pretty obvious that this is just poor design. There are too many gates and too many wires, and it's extremely inefficient to go through and troubleshoot it if it doesn't work correctly. This just demonstrates how incredibly important it is to simplify using Carnot maps and also using algebraic manipulation. Here we have the simplified versions of the circuit that we had. Each one of the solutions is the exact same circuit, but they've been simplified through the algebraic manipulation that we performed earlier. On the left is the algebraic manipulation implemented exactly as is. In other words, put in exactly how we simplified it before. We can see that it is much easier to see, much easier to read, and it is much easier to troubleshoot if we can't find the reason why it isn't working. We see below, on the bottom left, that it requires 3 7400 parts in order to create that circuit. However, if we look up at the top right, it's the same circuit just implemented with only NAND gates. If we look below that, we can see that this only requires 1 7400 part. This means that it's going to be the cheapest, easiest, and fastest to use only NAND gates to implement the circuit and to implement the truth table that we created at the beginning. This goes to show that not only are Carnot maps extremely important, but they also help us in terms of figuring out which would be the fastest and easiest way to implement any given truth table in any circuit.
So to conclude, using Carnot maps is an efficient way of simplifying Boolean equations, often faster than using reduction theorems. Simplified equations reduce the number of gates needed, and having a smaller number of gates, especially when using NAND gates, reduces the cost of a system. But why does any of this matter? Well, Carnot maps and the tools associated with them help save time, and time is money. The less amount of gates, the faster a system can run, and the cheaper it is to produce. You want your smartphone to be thin and fast, right? Thank you for watching. We hope this presentation has helped you understand the great value of using Carnot maps.